Hello everyone, I am Dr. Fawzul Atiq. I am giving some series of lecture for the course Discrete Mathematics. So we are in the first unit and the unit name is the Foundations, Logic and Proof. So in the previous lecture, we discussed about the De Morgan's law for quantifiers, right? And then the nested quantifiers, negating nested quantifiers, negating quantified statement, this kind of thing we have learned. So in today's class, we will do some conversion, like from mathematical expression to the logical expression, and then English sentence to logical sentence, logical to English. This kind of thing we will be doing because that we require in your real life. You may have to deal with the English sentence. So how you will make it in a logical way, right? Let us see. Okay. So translating mathematical statement into statement involving nested quantifiers. And nested quantifiers means what? That like more than one quantifier should be involved, right? So like one quantifier is within the scope of the other. So we'll see. So look at the first example. The sum of two positive integers is always positive. Now this is an English sentence and we know this is a true statement. You have to make it in a logical way, right? You have to make it in a mathematical way, that statement involving nested quantifiers. So how do you do that? So what to do? But this statement is true for all integers, right? For all any two integers. So what we'll do? We'll say that for all x, we'll say that for all x and for all y, right? So this any two integers we have considered, and then two positive integers. So if x and y are greater than 0, so how can you write? If x greater than 0 and y greater than 0, then what will happen? Then your things is this will imply that basically this all together, both of them together will imply that their sum is also greater than 0. Correct? So this way you can write. I think this color does not look good. I'll take a little deep color. Okay. Now this one we have done, and then because you have involved this kind of expressions, we have to inform that what is x and y. So in this case, the domain for both the variables are consist of all integers. Right. Now you can also restrict the domain. Right. What we can do, we can make for all x greater than 0, for all y greater than 0, x plus y greater than 0. That way also one can do. You can also mention it in a domain version, like what you can do, that for all x, for all y, you can directly write x plus y is greater than 0. But when? In this case, you have to specify what is the domain. Here the domain is set of all positive integers. Now you change it to from integer to positive integer, right? So this is what you will have. Yeah, as we mentioned this one. And if we make it even very small, shortly, that for all x, for all y, x plus y greater than 0, where the domain for both variable consists of all positive integers. Done. Okay, now we'll have another example. Before that, we should know that what is multiplicative inverse of a real number. So a multiplicative inverse of a real number x is a real number y such that x into y is equal to 1. So for any real number, multiplicative real number exists, but that real number should not be 0. Then you take any real number. Suppose you take 5. Then you have another, its inverse, which is 1 by 5, such that 5 into 1 by 5 is equal to 1. Right? So in this way, you can define the multiplicative inverse. And for then we have this expression, this sentence. Every real number except 0 has a multiplicative inverse. Yes. So any real number will have a multiplicative inverse. But the question is how you can write this as a statement involving nested quantifiers. So some mathematical expression you need. How to do that? So you guess. Now this is true for every real number, right? But except 0, this part is also there. Then it will have a multiplicative inverse. So how do you do that? So you say that for all x, because it is true for every real number, but there is a condition when it will happen, if x not equal to 0. Then it will imply that there exists a multiplicative inverse. So there exists a real number y such that it is a multiplicative inverse. That means x into y is equal to 1. Done. Where the domain for both the variable consists of all real numbers. We are done with that. I hope this is clear. Okay. So this is what we have done. Now we'll have another example. Okay, so this is a very interesting one. We are going to use it in different way as well, because it's a very good example of mathematical sentence and you have to make it in a like logical expression. So how do you do that? The question is, use quantifiers to express the definition of the limit of a real valued function fx of a real variable x at a point A in its domain. So this is basically the limit definition. Right. So many of you who has learned calculus little more, then they must have learned that what is the limit definition, epsilon delta definition. We call them as epsilon delta definition. So what is that? And even if you have not learned, no problem. I'm going to explain you what is that. So here the question is, we all know that how you write the limit. So limit of maybe x tending to a fx is equal to L. Suppose this is the limit is there and limit exists. So limit extending to a fx is equal to L. Then how do you define it mathematically? So mathematically, it will say that for every real number epsilon greater than 0, there exists a real number delta greater than 0 such that mod of fx minus L is less than epsilon whenever mod of x minus A is less than delta. So this is the mathematical definition. I'll show you. I have it already. Yeah, look at that. So this is the limit expression, but mathematically how you will define? For every real number epsilon greater than 0, there exists a real number delta greater than 0 such that mod of fx minus L is less than epsilon whenever 0 less than mod x minus A less than delta. Correct? So this is the mathematical definition. We call it as a epsilon delta definition. Now just you understand that, or maybe you think that this expression is given, this mathematical statement is given, you have to make it in a logical expression involving some quantifiers. So how do you do that? So you can easily do, now see that for every real number epsilon greater than 0, so we can easily make for all epsilon greater than 0, then there exists a real number delta greater than 0. So you'll say there exists delta greater than 0 such that this. But before that, I want to say that there is some role of x also, right? What is that x? X can be any real number. So that part also you have to involve. So this is true for every x. So then for all x, for all real number x, it will happen, right? And then this condition. Now observe this condition carefully. It says that mod of fx minus x is less than epsilon whenever 0 less than mod x minus a less than delta. Whenever this will happen whenever this will happen. Suppose this is q and this is p. What does it mean? It means that q will happen whenever p will happen, right? So basically it means that p implies q, isn't it? It's not that q imply p, it is p imply q. So q will happen whenever p will happen. Therefore p imply q. So that part we will do. So what is p here? P is this one. So 0 less than mod of x minus a less than delta. This whole thing will imply that mod of fx minus L is less than epsilon. We are done. And only one thing you have to mention, where the domain for the variables x, epsilon and delta are all real numbers. We are done. This is how you can express that limit exists at a point A and the limit is L using nested quantifiers statement. I hope this is clear. And we are going to use it. Now, one thing also you observe that here, for all epsilon greater than 0 and delta greater than 0, these are all restricted domain. Right? We could have mentioned it in the domain part also that for the variable x is real number and epsilon and delta are for epsilon and delta domain is positive real numbers. We could have mentioned there also, but we want to make it common. So therefore, epsilon greater than 0 and delta greater than 0 as the restricted domain. I hope you understand. Okay. Next, we move to the next example. Yeah, this one we have already done. You can see that whole thing in a very formal way it is written. Now, we will have some nested quantifier statement and you have to make it in a English sentence, right? So, because logical way it is written and you have to understand what it is written, right? What is the meaning of it, inner meaning of it. So let us see. Look at this example. Translate the statement for all x, then cx or there exists y, cy and fxy, where cx is x has a computer, fxy is x and y are friends, and domain for both variable x and y consists of all students in your school. So how do you explain this thing? What does it mean? Now see what is written. It is written that for all x, that means for every student in your school, then either cx, that means either x has a computer or there exists a student y such that y has a computer and x and y are friend. This is what it is, right? So for every student x, either x has a computer or there is a student y such that y has a computer and x and y are friend. This is what it is saying. Sorry, just a minute. Yeah. So the one way this part is done, but you can even simplify this. You can say that every student in your class has a computer or has a friend who has a computer. Easily you can say. So you can make it even simpler. The statement you can make it even simpler. You can say that every student in your class has a computer or has a friend who has a computer. Done. So this things is actually meaning this sentence. I hope this is clear, right? So observe the statement carefully, then understand through the just by reading the quantified statement, and then finally you understand what it actually meaning. We have another example which is little bigger but very interesting as well, and it is like it triply quantified, right? Three quantifiers involved in it, triply quantified. So how do we do that? What does it mean? So here, if AB means A and B are friends, so only one propositional function is involved, having two variables. So if AB means A and B are friends, then just read it. It says that there exists X and X, Y, Z are all real number, right? So there is a student in our school for which, for every student Y and every student Z, if, this is the if part. So if X and Y are friend and X and Z are friend and Y and Z are different, then it will imply that Y and Z are not friend, isn't it? So there exists a student X in your school for which, for every student Y and every student Z, if X and Y are friend, X and Z are friend, and Y and Z are different student, then it will imply that Y and Z are not friend. This is what it says, right? You can see that. But finally, you can even you can make it more simpler. What is the final meaning of it? It says that there is a student in your school, none of whose friends are also friend with each other. So there is a student in your school, none of whose friends are friends with each other. Got it? So this is the final meaning of this logical sentence. So in other words, there is a student, none of whose friends are also friends with each other. Done. Okay. Now there is a lot of big mathematical statement involved, right? You have to prove that, you have to write it in a logical expression. So if a person is female and is a parent, then this person is someone's mother. So this statement you have to make it into that a mathematical statement involving logical expression. So you may involve like whatever is needed, and or that quantified statement, anything, quantifiers, whatever needed, you can involve. By conditional statement, whatever you require. How do you do that? So your first job is, first you have to make some propositional function. What you need? If a person is female and is a parent, then this person is someone's mother. So there are three different things that you involve. Person is female, you require that. A person is a parent, that also required a propositional function, and then you require this person is someone's mother. So the person is someone's mother. So we need three propositional function. So I have read it or made it already. So you represent fx as x is a female. Your fx is such that x is female. you represent px as x is a parent, and you represent that mxy as x is the mother of y. So three propositional function we have written, right? This is x. Now how do you do that? It says that if a person is female and a parent, right? So that means, and this is true for her, this is true for every person, right? So what we'll do, we'll start with for all x, and then if for all person x, if the person is female and is a parent, right? How do you write that? So if fx and px, both of them are together happening, fx and px, so parent and female both, and then what will happen? So if a person is female and is a parent, then there must exist a child, correct, such that x is the mother of that child. That female person who is a parent is the mother of that child. So how do you do that? So there must exist a child. So how do you write? So there exists a y such that mxy, because x is the mother of y. So there exists a y such that mxy. We are done. Clear? You may also write it that for all x, there exists a y. Then if fx and px both are happening together, this will imply x is a mother of y. Done. So this is how you can make a English sentence. If a person is female and is a parent, then the person is someone's mother. You can write it in a logical way in this. This is the method. I hope this is clear and easy as well. Okay, now I have one more one. This one we have already discussed. Well, I have one more example. Express the statement that everyone has exactly one best friend. How do you write it? Everyone has exactly one best friend. As now you have to write this as a logical expression involving predicates, quantifiers with a domain consisting of people and logical connectives. So how do you do that? Everyone has exactly one best friend. So we need some propositional function again. So first let us define something. So suppose bxy is a statement such that x is a y is the best friend of x. bxy is such that y is the best friend of x. So you denote it in this way. Now, how do you write? Everyone has exactly one best friend. All of you try, make the video, pause and try. So everyone has exactly one best friend means exactly once. Have you heard these things in some quantified expression? Yes, uniqueness quantifier you have to involve. How do you do that? So this is true for everyone, right? So every student or everyone, so every person x, so for all x, then has exactly one. That means one unique best friend, right? So how do you do? So there exists an unique. This is the uniqueness quantifier. There exists unique best friend. So there exists a unique y such that y is the best friend of x. How do you write? B of xy. So therefore, this way you can say that everyone has uniquely one best friend or exactly one best friend. So what is the domain of it? Domain is the like all persons in the world, maybe consisting of, or domain consisting of all people. It is already there. I hope these are clear, easy. Okay, so this is, we have already done this one. Now negating nested quantifiers. Now what you have to do that, like some quantified statement you have to make the, what is the negation of it, right? So the first question is, it is given as for all x, there exists y, x into y is equal to 1. This is very, very easy. Now you have to negate it. So you have to, what is the negation of this expression? Negation means what? Just add a negation before that. Now what is the expression we are going to get it? Now negation of for all x you have. What will happen? We know De Morgan's law for quantifier. This will become there exists x. Then negation will appear here. Then negation of there exists y. What is that? So this negation will become for all y. Then negation will appear here. The negation of xy is equal to 1. What is the negation of xy is equal to 1? Negation of xy equal to 1 is x into y not equal to 1. We are done. Right? So we have done it in one line. You can easily understand. So for all x become negation of for all x become there exists become for all y, and this negation of xy equal to 1 become xy not equal to 1. We are done. Yeah, this is what you have. Then look at this example. Use quantifiers and predicates to express the fact that limit extending to a fx does not exist, where fx is a real valued function of a real variable x and a belong to the domain of f. How do you write it? So we have already expressed that what is limit exist expression. Limit exist. Right? We have done it in the few minutes back. So this is the limit exist expression. For every epsilon greater than 0, there exists a delta greater than 0. For all x, if you have 0 less than mod x minus a less than delta, then it will imply that fx minus l is less than epsilon. So this is the limit exist expression. We have already discussed in the previous few slides. Now you have to make limit does not exist. What does it mean? You have to take the negation of it. So negation of this one we have to discuss. What to do? Now, what I will do, I will first work on this expression, right? I will first work on this expression. This says this is P imply Q type, right? P imply Q type. And finally negation will appear before that. So what we'll do, first we'll work on this. So if I have P imply Q, we all know that it is equivalent to something. We said it several times. This is very, very important one, the implications law. What it says? It says that P imply Q is equivalent to not P or Q. Correct? So first we'll work on this inside portion thing, and then we'll work on the negation of the other thing. So I'm keeping it as it is, the other thing as it is. What I'm going to do, I'm keeping other things as it is. Only I'll work on the inside portion. So this will become negation of sorry, for all epsilon greater than 0, there exists delta greater than 0. Then for all x, then this will become not of, right? Because P imply Q is equivalent to not of P or Q. So what I will do, this is not of the inside portion 0 less than mod x minus a less than delta. Then imply will become or not of this or Q. Q is this one, whatever we had as it is. So fx minus L is less than epsilon. Done. So I just have worked on the inside portion. Now what to do? Now you apply the negation to it. So what will happen? This will happen as this is equivalent to now negation of for all epsilon. What will become? De Morgan's law quantifiers. It will become there exists epsilon greater than 0. And I mention it that this epsilon greater than 0 is the restricted domain. So you cannot say that there exists epsilon less than 0. No. This is just mean that restricted domain. It is only to mean that the domain for epsilon is the positive real number. Right? So we'll say there exists delta greater than epsilon greater than 0. We'll not change it here that epsilon less than 0. No. So there exists epsilon greater than 0. Then negation will appear here. So there exists or negation will appear here. So this will become there exists will become for all delta greater than 0. Then negation will appear here. For all x become there exists x, and then negation will appear here, this inside portion thing. What will happen? So the whole thing, something or something is there outside, there is it. So now, sorry, okay, all got this thing. I'm sorry, this some technical problem. What I will do that you may see that finally will have this P imply Q was there, right? Maybe I'll write it one more line. There is a technical fault. So I'm doing this one. Then there exists delta greater than 0 for all x. And this was negation of 0 less than mod x minus a less than delta. That imply that mod of fx minus L, sorry, minus L less than epsilon. So this is not this one, but this is this one. This is OR operator. So what we have done, we have done P imply Q was equivalent to not P or Q. But this negation, whenever it will appear here, so I'll just do one more time. So for all will become there exists epsilon greater than 0. There exists will become for all delta greater than 0. For all will become there exists x. Then negation will appear here. Now negation of these things, right? So negation of not P or Q. Negation of not P or Q is what? T Morgan's law for quantifier. So it will become P, negation P and negation Q, but it is already negation is there. So this will become negation of negation is what? It is the original one. So 0 less than mod x minus a less than delta. Then or will become and negation of this one. What is that? Negation of this one is fx mod of fx minus L is greater than or equal to epsilon. Our proof is done. This is what you have to prove. You have to say that this is the limit does not exist expression. Right? So I have already made it in a like explicit way. You can see this one. Make the video pause and you can see that whole thing is written in very explicitly. I hope this is clear. So all the content I have taken from this book only, Kenneth A. Rosen, Discrete Mathematics and its Applications. I hope you enjoyed the video. I hope you are feeling good about this course. This is not at all a difficult course. It's a very easy course, provided you are understanding that and you are practicing the basic things. Right? Thank you very much. If you like the video, if the videos are helpful, please give your feedback. Or if you want it in a different way, that also you can write it in the comment box. Thank you very much. We'll meet in the next video.